This one is just another alkene. It's trans-3-hexene, and so you get, you can see some of the differences, in particular that one there, which is out of that bending mode and lets you know for sure that this one is indeed trans. And I think that might be about what I wanted to show you. Also, oh yeah, this too. Notice that because of the nature of this particular alkene, it's very well balanced. There's a lot of symmetry. Because of that symmetry, there's not much of a dipole here. And without much of a dipole, you don't get much of a peak. All right? So you don't always see the CC double bond peak at about 1600. But you do get this one. And again, as close as it is to 3000, it is just to the left. Okay, you guys all see that? I didn't put the red line up there because it would overshadow some of the points. And I think that's the only purpose to show you this slide. Here's an important one. You see the most obvious thing about the alcohol that's different from the other spectra we just looked at? Right? Notice this shape. We call that a broad, strong IR absorption, right? Strong because it's dipping down into the bottom third, and it's broad. Notice how it just looks different from the CH stretch right next to it, right? The CH stretch comes pretty much straight down and then goes straight back up to the baseline. The OH doesn't. It kind of takes its time getting there and then going back. Now, a simple explanation for that is hydrogen bonding, frankly. All alcohols are hydrogen bonding with each other when they're mixed into either solution or just together taking an IR pure. But because of the hydrogen bonding, a lot of things are going on as far as exactly where the hydrogen is relative to the oxygen. There's a lot of changes in bond length, things like that. And so the OH will always appear this way unless you do something specific to make it look otherwise. So when it comes to alcohols, now here's a peak. Again, first pass. You're looking at a test question. Here's a spectrum. Here's a choice of compounds. You see that. What do you say to yourself? Where's the alcohol? If there's only one alcohol on the list, you're done. If there are two, you got to look for something else. Other things. Well, probably the most important other thing is this one. That's the CO stretch. It's labeled up here at being between 1050 and 1200. And also, that would show up in the case of alcohols and ethers, right? Ethers also have a CO bond, but ethers lack, obviously, the OH bond. So an ether wouldn't have this, but it would have this, okay? Now, here again, sometimes you need to dig deeper. So I'll tell you about the CO peak in a way in which you may have to dig deeper. Primary, secondary, and tertiary alcohols all have a characteristic absorption. 1050 should correspond to primary. Check the book. My numbers might be off a little bit, but it's there. And the secondary one will be different. It will be like 1000. Tertiary is like 1150. And if it were to happen to be attached to an aromatic ring, it would be different still. So if you can, and it would be the specific number that corresponds to that peak, okay? But most of the time, this is all you need. If you got a choice between alcohols, then you might need this. The other one that you're guaranteed to see from time to time. C double bond O, it's a carbonyl. This is where I ask you guys to remind yourselves really about the functional groups, because C double bond O is actually a part of several functional groups. Now carbonyls more specifically refer to aldehydes and ketones, but you will also find a C double bond O as part of carboxylic acids, esters, amides, okay? So it appears in other functional groups as well. To this point, really ketones and aldehydes are what you've seen the most when it comes to carbonyls. And that's okay. That's been the exposure up to now. So the compound that you're seeing the IR for is this one here. Looks like butanol. And in particular, it's an aldehyde, right? You know an aldehyde because, right, I should say you know an aldehyde is different from a ketone because of the hydrogen that's attached to the carbon that's double bonded to the oxygen, right? Aldehydes have a particular extra peak that ketones will not have because of that H. And it's right there. Something to keep in mind. It's a way to tell difference between aldehydes and ketones. That's just about 2,700.